Hello there and welcome to another video on module 5. Since we discussed the previous topics, in this one we'll be referring to vector processing. Okay, and let's continue with it. So the two topics that will be covered in this video are vector processing and array processing. Fine. Vector processing is a class, like there is a class of computational problems that are beyond the capabilities of conventional computers. This basically means that there are many computational problems that are too big for a normal computer to compute them, because it may take even days or weeks for it to complete. Fine. So in many of these applications, these such problems can then be solved in terms of vectors and matrices. Fine. And these vectors and matrices are then solved using vector processing. So these are just the applications for vector processing. You can go through them. The basic operation of vector processing. Okay, so what happens is a vector, the definition of a vector is an ordered set of 1D array of data items. So if v is a vector of n length, then it is represented by v equals to v1, v2, v3 all the way to vn. Fine. So if n is 100, so it goes from v1 all the way to v100. The element vi, okay, so the ith element of v is written as vi, and the index I is what refers to the memory address or the register where it has been stored. Fine. So v1 will be the written as v1, okay, and the index 1 will represent the memory address or the register, that means r1, where it is stored. We consider a basic program, okay, in assembly language where a and b are vectors of the size 100. That means 100 elements in a and in b. Their sum is put into vector c. So the basic program would be initializing I to 0, reading a, I, b, I, fine, storing it in c, the sum of a and b, storing it in c, incrementing I, and then going from 0 to 100 and then continuing. So this is a loop that would run. Okay, if I is less than 100, it will go back to a, it will read a, and then guess. So you see, when this loop is run, it goes 100 times. Fine. This is going to take a lot of time for the PC. Okay, so what we do is the vector processing computer eliminates the overhead. Fine. So what it does is there is only one instruction that completes the entire code. Fine. So the vector instruction is made as C 1 to 100, A 1 to 100 plus B 1 to 100. So this one single line replaces the entire loop. What it does is it tells the computer, the vector processing, that C has elements from 1 to 100, A has from 1 to 100, and B has from 1 to 100. You have to add each vector to each of them and then store them in the respective points. So A1 and B1 will be added and stored to C1. Same way A2, B2, all the way till A100, B100, stored to C100. Fine. So yeah, the instruction format of a vector processor is in this way. Okay, this is the operation code, the base address of source 1 and source 2. So the address of A will be here, the address of B will be here, the base address destination, okay, the base address of the destination, sorry, okay. So C, the address of C will be stored here, and then the length n. So we had 100 in the previous example, so that's how the length will be stored. Fine. And the instruction format, okay, it assumes that vector operands reside in the memory. Fine. So it is also possible to design a processor with large number of registers and store all the operands in registers prior to the addition operation. Fine. So before we initiate the addition, we can store all the data in registers. Okay, and then in that case, the base address and the length, okay, of the instruction would specify not the address but rather a group of registers. This is just another way of storing the data. So we can consider matrix multiplication as an example, right? So this also has a large number of its two matrices multiplying. So it is, for a basic program, it's going to be huge and it's going to be time taking. Fine. So the 3 by 3 matrix is multiplied by this formula, okay, where A of ik is multiplied by B of kj. Fine. So this requires 3 multiplications and the 3 additions. Okay, the total number of multiplication or additions required is 3 into 9, so that will be 27 different operations to be performed. Okay, The general inner product consists of the sum of k product terms of the form this. Okay. So basically what we discussed previously is that we understand in matrix addition it requires a lot of multiplication and addition operations together, okay, which would take the normal processing a huge time. So what happens in the parallel processing is that we have source A and B, the values of A and B into the multiplier, fine. We multiply the values in the pipeline and then we add. So these are pipeline segments, fine. 4 segments of the multiplier and then 4 segments of the adder. What happens next is we are to perform these functions a1 b1 a5 b5 a9 b9. Okay, you can consider them a1 b1 a2 b2. These are multiplication and additions to find the matrix multiplication. Okay, so the partial sum are added to form the final sum. Thus what the pipeline does is this is how it calculates the inner product. Fine. Floating point multiplier pipeline has 4 segments and floating point adder pipeline has 4 segments. Okay, so C, our function C is a1 b1 plus a2 b2 plus a3 b3 all the way to ak bk. So in the first clock input we are inputting a1 and b1 into the multiplier pipeline, fine. After the fourth we have inputted all the values, okay, from a1 to a4, okay, not all but from a1 to a4 for the fourth clock cycle. At the 8th our adder pipeline is also completed, so the additions, the multiplication for these 4 sets is done, addition for these 4 are done, and then at the 9th, 10th and 11th cycle we are getting outputs, fine. So at the 9th cycle our output is a1 a1 b1, the multiple of a1 b1, okay, and the sum of a5 b5, okay, a1 b1 multiplied and then a5 b5 multiplied and then their sum, okay, is made. So this is the output a1 b1 a5 b5, and then at the 10th cycle we are getting a2 b2 multiplied by a6 b6. Okay, so this is how they're executed: a1 b1 plus a5 b5, a2 b2 plus a6 b6, a3 b3 plus a7 b7, and so on. This is how these cycles, okay, after 4 clock cycles, okay, 9th, 11th and 12th, okay, we are going to get outputs for this, and then it's going to repeat again for k values. The next is array processor. So basically array processor is just a subtopic of vector processing. An array processor is a processor that performs computations on large arrays of data, just like matrices, vectors, arrays, fine. There are two different types. One is attached array processor and a SIMD array processor, fine. The attached array processor is basically a peripheral, okay, for a basic computer, fine. So a general computer system can have this array processor attached as an auxiliary, and then this enhances the performance of the computer by allowing it to do vector processing, okay. Thus the computer becomes capable of performing parallel processing with multiple functional units. This is how it is attached. So this is the main memory and the local memory. They are connected with a high speed memory to bus, okay, a memory to memory bus, sorry, a bus system is used, common bus system. The general purpose computer, we have it here, and the array processor, attached array processor, is connected to the local memory and the input output interface of the general computer, fine. And so it works this way. So in this we can see that the array processor is connected to the input output controller, fine. Computer treats it as an external interface. Data is transferred to the array processor from the main memory, okay, into the local memory using the high speed bus, and well, it helps in performing complex arithmetic applications through vector processing. Okay, the SIMD array processor on the other hand is a processor that has multiple processing units, fine, and it operates in parallel. The processing units are synchronized, okay, for doing the same task under the common control unit. So there is one control unit but multiple processor units, okay. Each processor element PE includes an ALU of its own, okay, a floating point arithmetic unit and a working register, okay. So there is a register plus it has a local memory M. You can see through this diagram how an SIMD array processor is organized. So there is a master control unit, okay, so all PEs are connected with a single master control unit. There is a main memory that is connected to the local memory of the PE, okay. It has its own ALU and registers, so it takes data from the local memory okay, which gets its data from the master memory, the main memory, and they are controlled using a simple main control unit, okay. And this is how an SIMD array processor works and how it's organized. So the main memory is used for storing the program, okay. The master control controls the operation of the processor elements, and it decodes the instruction, okay, thus allowing the determination of how the instruction is executed. Each processor element uses operands stored in its local memory in the memory named M, okay, and then vector operands are distributed to local memories prior to the execution of the instruction. So first the operands are stored in the local memory, and then we execute the instruction. That's it, and see you in the next video.